Okay, what is fluid pressure? Let's take a look at this question and maybe it'll make sense to you. If you were going to sit on one of these seats, now hopefully you can see what it is. If I'm going to watch a movie in a movie theater, would you be cool with sitting in one of these nice comfy chairs or on a bike seat for, say, 2 hours? Now, of course, everybody's going to say the movie theater seat, but why is that? Well, the idea here is the area that you have to work with. This is nice, huge, comfy area for your entire force, your entire weight to sit on. Riding a bike for 2 hours versus sitting in a movie theater seat for 2 hours are two different things. And it all has to do with something called pressure. And what is pressure? That's the question. Pressure is the result of a force distributed over an area. So, in the case of what we're just talking about, the force was your weight. Your weight is the force. And it's distributed over an area. This area right here, you could have a big area like the movie theater seat, or you could have a small area. Okay? So, the unit of force is something we call a newton. We've talked about this before, a newton, and our abbreviation is big N. The unit of measurement, or the SI unit for area, is meters squared, or square meter. So that means that we're going to go ahead and assign pressure a new SI unit, which we call a Pascal. Now, Pascal is a unit that's named after Pascal, and all it is 1 Newton per square meter. So that's exactly what it is. What is your force, which is in newtons, divided by your meters squared? And so it basically is a fraction if you think about it. So if we look at this here, if an area of a box touches the ground is 1.5 square meters, and it has a weight. Now this weight right here is a force, okay? It is a force. So all we have to do is say, okay, what's our equation look like? In this case, our equation looks like this. So we would take the force, which is 2,700, and put it right there. We take 1.5, which is the area, and put it on bottom. When we plug that into our calculator, then we can easily see that this is 1,800 newtons per meter squared. Now we just learned that this number right here, or this unit right here, equals the same thing as a Pascal. And since this is such a large number, then we could actually turn it into kilopascals. Or remember, 1,000 pascals equals 1 kilopascal, just like kilometers or kilograms. And so we're going to get into something called fluids because we're talking about fluid pressure. So now that we kind of know what pressure is, let's talk about fluids. So if we look at what is a fluid is a substance that takes on the shape of a container. Both liquids and gases are fluids. So a lot of people understand, well, liquid is a fluid, that makes sense. But gases are fluids also. So we have examples like water, oil, gasoline are all liquids that make sense to us. Then also air, which is what we are breathing in, and helium, which is in a balloon. Those are also fluids because they take on the shape of the container. That's important. So if we look at this here, particles in a liquid are tightly packed together but slide around. Particles in a gas are far apart and travel in straight lines until they collide with each other. This is a beaker of liquid here. You can see they kind of slide up around each other. And here's a little container of gas. And they just basically, it says, they go in straight lines until they run in. So if this is going to go a straight line, and then it's going to hit another molecule, and it's going to bounce over here and go to another straight line until it hits. It's kind of like a little game of pool. They just kind of go at little collisions. So collisions over here, sliding over here. That's the major difference between the two. Pressure and fluids. So now we're combining what we know about pressure with what we know about fluids. And we can say that water in a glass is in contact with the walls and the bottom of the glass. That makes sense. So this green liquid is it's touching on the bottom and on the sides. So because of that, it's exerting a pressure. And for fluid that is not moving, depth and the type of fluid are two factors that determine. So what type of fluid you're dealing with is going to determine what type of pressure you have, along with how deep it is. And that's why it's kind of tough to think about, but if you were to dive in the ocean and go really deep, it would actually be very dangerous to you if you don't have the proper equipment. And maybe you've jumped into a pond or a lake and gone down really deep, and maybe your head starts to feel a little goofy. And there's a good reason for that. Each vase holds a different amount of liquid. The liquid levels are all not the same because the pressure actually depends on depth, not necessarily the amount. What about planetary atmospheres? The layer of gases surround a planet is known as an atmosphere. We're pretty aware of our atmosphere. All planets in our solar system have some form of atmosphere. So that's all planets. We're definitely aware of what's going on here on Earth, but we know from sending probes to other planets in the solar system, they do too. The weight of the atmosphere creates atmospheric pressure at the planet's surface. Kind of look at this here. It says which planet listed in the table has the greatest atmospheric pressure. So you're kind of looking at this and thinking through this. That would be Venus because of this right here. It's a huge atmospheric pressure. What chemicals substance exists in all but one of the atmospheres? So look at all the different ones. Which one is all but one? That would be nitrogen. As you can see, it's here, and it's here, but not mercury. The bar is another unit pressure, just like a Pascal. We have all kinds of measurements actually, torrs, bars, PSI. Convert each of the given pressures into bars. We could simply use this right here as a unit of multiplier. So just take that, turn it into that. So we can do that. So for like example, for Earth here, 101, we know that 1 bar equals 101.3, so that's just 1. So we'd say that we divide it by this, we go 101.3 kilopascals in the denominator, and then 1 bar on top. And when we multiply by this unit multiplier, that would cancel this out right here and give us 1 bar. And actually, you just do that for every one of these. And that's how we got the unit. How much force is exerted on 2 square meter? So the force, remember, pressure equals force divided by area. So we could simply do that, a little rearrangement, and multiply that by 2 by rearranging the equation. So again, we can just do all kinds of different manipulations of these right here. Well, this should actually be a 5 right here. I'm not sure why it says 3. On which planet would a balloon filled with a given quantity of helium have the smallest volume? And that would be Venus, because Venus has the greatest pressure. It would actually kind of smush it down. Air pressure on Earth is what we care about the most. Probably don't care about air pressure on Venus very much. No offense, Venus, but we live here. The Earth's atmosphere exerts pressure of 101 kilopascals at sea level. That's a lot. That's like the force of a small moving truck. Why aren't you crushed by the air pressure? Well, a lot of it has to do with the fact that the same pressure is inside of your body. You have huge pressure inside of your body. And because of that, the balanced forces cancel out, and you have a net force of 0, which is great. You may notice when you go up hills, when you're driving in the mountains or up a roller coaster or maybe even on an airplane, that your ears pop. Your ears are popping because less atmosphere or more atmosphere is happening at a rapid pace. So you feel the difference very, very abruptly, and your body has to do something. And so we know that there's a lot of pressure in your body and it's being released. And this is pretty neat too. If we took a can and heated it up, we put a little bit of water, just enough in the bottom right here, and we heat it up. And if it says as a can, then the can is capped. As the can cools, the pressure inside the can becomes less than the outside. The difference in the pressure can actually end up crushing the can, which is pretty cool stuff. Because the pressure's changed, because the temperature's changed, because the speed has changed. So that's pretty exciting. This is just kind of a beginning of the unit, or excuse me, the chapter that covers pressure and fluids. But it's a pretty good starting point.